Introduction of Professor Arghode. Dr. Arghode is currently the Assistant Professor in the Department of Aerospace Engineering, IIT Kanpur. He received his PhD in Mechanical Engineering 2011 from University of Maryland. His research interests are the field of advanced gas turbine combustors, reacting flow for the aerospace application, turbine blade cooling, and thermal management of aerospace system. Please.
Thank you for the introduction. And today I'll talk about investigation of forward and reverse flow CDC combustors. So basically the talk will cover the influence of flow field and what it does to combustion characteristics for CDC combustors. So Dr. Gupta, the work was done at University of Maryland at the combustion lab under supervision of Dr. Ashwani Gupta. So here's the outline of my presentation. So I'll briefly introduce what is high temperature air combustion, which is the basis of CDC combustor, and we derived the features from HITAC combustors. And then we went towards CDC combustors, and I'll briefly introduce what are the salient features of CDC combustors, and briefly report different geometries in the literature. So they have used different flow schemes, forward flow, reverse flow, and then different fuel injections. So I'll briefly discuss some geometries reported in the literature, and then I'll talk about results of forward and reverse flow geometries with respect to flow field, reaction zone location, and emissions. And then finally I'll conclude. So high temperature air combustion, the work started in early 1990s. It has been almost 25 years now, and then it was successfully demonstrated for furnace application. So for furnaces, one important thing to note is that they have large volume, so the amount of heat released per unit volume is pretty low. Mostly less than 1 megawatt per meter cube. And here is the difference between ordinary combustion and high temperature air combustion. So in ordinary combustion, you have fuel jet coming in, and then air jet is in a close vicinity of fuel jet. You have a bluff body stabilizer, and as the fuel jet comes in, and then it mixes with the air jets and forms a stoichiometric flame zone or diffusion flame, which is represented here as F star A, and then this diffusion flame has high temperature. So because it is stoichiometric, its peak temperatures are close to adiabatic flame temperature at equivalence ratio of 1. But in high temperature air combustion, what you do is you extract some of the heat from the exhaust, you preheat the air, and then in one of the early definitions, you want to preheat the air above the auto ignition temperature of the fuel. So technically you don't need to ignite the fuel. It is automatically above the auto ignition temperature. And you separate fuel and air streams. So if your fuel and air streams are separate, then it does not come in direct contact with air, and you do not form this high temperature zone. So your air stream will also entrain the burn gases, fuel stream will entrain the burn gases, and somewhere in downstream you will have this distributed reaction zone. So this B star, F star, BH, and then you have avoided the high temperature zone. So that's how you achieve more uniformly distributed reactions. And benefits, because you are extracting energy from exhaust, you definitely get energy savings, and other important benefits are you have very low pollutant emissions, mentioned very uniform thermal field, large reaction volume, and in this case you don't require any flame stabilizer, so you are actually directly injecting fuel and air inside the volume, so you don't have any swirler or any bluff body, so to say. So basically for high temperature air combustion, you are operating at low oxygen concentration because you are entraining a lot of burn gases, and Dr. Gupta talked a little bit about internal entrainment effects. You reduce the oxygen concentration and then your temperatures are high. So high temperature air combustion flames are mostly operating in above the auto ignition temperature regimes. And here are some of the photographs. So I mean, this was some fundamental flame studies done at Dr. Gupta's lab. I mean, your flames are mostly at lower oxygen concentration and higher temperatures. So also known as flameless oxidation, mild combustion. I mean, many other names have been suggested for this sort of flames. So with this background, we started this work of CDC almost 10 years back in 2006. And so our objective was to develop combustors which have similar features of HITAC combustors, but they operate at higher thermal intensities, maybe more than 15 megawatt per meter cube. And we went up to almost 400 megawatt per meter cube, but I'm not going to talk about the role of thermal intensity. And some of the features which we preserved from HITAC combustion is we want to discretely and directly inject air and fuel inside the combustor. So directly we have this air and fuel jet which is injecting inside the combustor, and then we need to integrate all other stuff, like we should have supportive gas recirculation inside the combustion chamber, and then your fuel should mix with the oxidizer sufficiently fast. And so there are many different aspects of designing the CDC combustor, but here I will only mostly talk about the influence of flow configuration. Come to it, what do I mean by different flow configurations? So some of the important factors which we need to keep in mind before designing CDC combustors is we need to have sufficient gas recirculation so that your temperatures are high, and then it will support the ignition and combustion inside the chamber, and your fuel jet should mix pretty quickly with the oxidizer. Your thermal intensity should be high enough so that it is a representative of gas turbine combustors. But here I'll talk about different flow configurations. So I mean, you have an air jet, you have a fuel jet, and one exit from the combustor. So there can be different combinations of air and fuel injection. So I am classifying these into two categories: forward flow and reverse flow. And in forward flow, your bulk flow is in one direction, so your air mass flow rate will be almost 20-30 times your fuel mass flow rate. So if you are injecting air from opposite end of the combustor exit, so that's what I'm classifying as forward flow. And in reverse flow, the air jet is on the same side of the exit, and your bulk flow has to take a complete U-turn and then exit the combustor. And then another variable is your fuel jet. So your fuel jet you can put on the same side of the air jet or the opposite side of air jet. And in reverse flow, we also investigated the cross flow or cross injection of fuel. So your fuel can be in cross flow of air jet, and then we'll come to it. I mean, later on we found that because of this cross flow, we get better mixing and better combustion and emission characteristics. And for all the cases, we have premixed modes as a baseline. So your premixed mode are supposed to give you lowest NOx emissions, so that provides a baseline to compare all other non-premixed modes. So I mean, the basic idea is if you can achieve characteristics which are closer to premixed flame in your non-premixed combustor, then you avoid some of the undesirable characteristics like flame flashback. So a quick snapshot of different geometries which have been reported in literature. So these top geometries are some of the geometries for forward flow configuration, and then the bottom ones are for reverse flow. So one thing we noted was that, I mean, there have been different forward and reverse flow geometries, but in a single geometry they did not compare like what is the influence of flow configuration of different geometries, not very extensively to say. I mean, so they have one geometry and then they report results for that particular geometry. So we found out that, I mean, there are all these different geometries which have been reported, but I mean, to compare on a same platform, it will be useful. So that's what we tried to do in this work. So this is the test facility, around 3 inches by 3 inches size, very simple facility. We have a single air injection port, single fuel injection port, just jets coming inside the combustion volume, and then burned gases exiting from the combustor. And in the same geometry, we modified it a little bit so that we can incorporate the cross-flowing, cross injection of fuel also. So in this geometry, I reduced the volume by almost half so that my thermal intensity is almost 2 times, and then I can inject fuel in the cross flow. And one thing to note here is that this combustor does not support direct injection. So you need to have a pilot flame, a startup flame initially, and then you slowly transition into this direct injection CDC mode. So in all the cases, your air and fuel temperatures are at room temperature, and to vary the equivalence ratio, I am actually varying the air mass flow rate. So I am keeping the fuel mass flow rate constant, and all are at 6.25 kilowatt. So first, forward flow configuration. So we investigated 5 configurations, including the premix mode. So again, in forward flow configuration, again I can inject air from the center or air from the side. So I'm just naming it as FS and FS2. And in premix mode also I can inject air from the center, air and fuel of the center, and then air and fuel from the side. So these gives me different forward flow configurations. So we did very simple CFD analysis using commercial code. These are for non-reacting flow cases, and then we just wanted to see what happens to these jets in the cold flow simulation. So in this case, if your air is injected from the center, if your exhaust is offset, so it is not symmetric, then what happens is that, I mean, there is a pressure difference. So air tries to entrain gases from the side, so there will be lower pressure inside this region. But as the exhaust is on one side, so pressure here will be slightly higher than this. So that's why the jet actually turns on one side. So it almost turns, everything turns on one side. So this was very interesting result which we observed. And if you inject air from the side, it again splits into 2 parts, and one part actually directly escapes from the burn gas from the exit, and one part turns to the left side. But point to note here is that the fuel jet, I mean, here the fuel jet is seeing the cross flow, it gets mixed faster. Here also it is seeing faster cross flow, it gets mixed faster. But in this case, this fuel jet is not seeing any strong cross flow. So, I mean, later on we'll see that, I mean, this configuration was not able to sustain the flame. So if I do the center line velocity decay, I mean, air jet decay was almost same for all the cases, but fuel jet decay for this case was very, very delayed. So that also means that your fuel mixing is retarded to a large extent. And gas recirculation, so for configuration FS2, we saw that the air jet actually turns and then directly escapes from the burn gases. So here you have less gas recirculation for this configuration FS2. And if I calculate the fraction of gases which are recirculated from the fuel side, so if I'm injecting air from here, so right side is the fuel side. So for configuration FS2, I mean, most of the gases, almost half of the gases are recirculating from left side, half from the right side. So this configuration also had very less amount of gases which are recirculating from the fuel side. So combining all these, I mean, we also found experimentally that this configuration was not supporting combustion. So this also means that, I mean, you just don't have to inject directly air and fuel. You have to make sure that you have proper flow field distribution and proper gas recirculation to sustain combustion. And we also did residence time distribution characterization for these 2 configurations. So if I assume that my reaction zone is closer to my fuel jet, and if so after converging my cold flow solution, if I put a step at the fuel inlet, if I put a step input of tracer and then see how the tracer comes out, it will give me the residence time distribution of the tracer at the exit. And so even though your average residence time will be same for these 2 cases, in this case your tracer will try to escape faster. So large amount of tracer will try to escape quicker, and then it may give higher CO levels. So coming to the OS star chemiluminescence distribution to see where your reaction zone is. So at first instant, we can note that the reaction zone is actually moving around inside the combustion chamber, and that may not be very useful. I mean, if you are designing a combustor liner which is cooled by air, then if your reaction zone is moving around, then it is a big problem for cooling the combustion liner. And second thing is, I mean, these shows very different patterns. I mean, here if I increase the air mass flow rate, the reaction zone is actually getting pushed towards the left side, but here your reaction zone is actually coming towards the air jet, and that is possibly because if your air jet momentum is higher, it will try to entrain the fuel jet faster and then try to bring the reaction zone closer to the fuel jet. So here if I do residence time calculation, I think it will have lower residence time than this case. So this configuration FS may give higher CO levels. So in the end we'll come to the NO and CO levels, but I'll just talk about reverse flow configurations. So in reverse flow configurations, again we investigated configuration RO and RS, where fuel is on the same side and fuel is on the other side, and then later on we switched to reverse cross flow configuration, where fuel is injected in the cross flow, and then we wanted to see what it does to combustion characteristics. So again, very simple CFD for the flow field in cold flow simulation. So here we'll see that as I'm injecting this air jet, again it is splitting into two parts. So one part is going on the left side, mostly it is not doing much. The one part is splitting to the right side, and then this is providing the cross flow to this fuel jet so that it can mix faster. But there is no cross flowing air for this fuel jet to see. So I mean, this fuel jet does not get mixed properly, and then we also observed that this cannot sustain reactions. And then one thing to do is to eliminate this recirculation. We can reduce this dimension, and then if I reduce this dimension, then I observed that most of the gases are recirculating from the right. So possibly that will be more beneficial. Again, so air jet decay, not much difference, but fuel jet decay, again, for this case, RS, the decay was much delayed, and that also suggested that, I mean, this configuration RS cannot sustain the flame experimentally. So we could not sustain the flame in this configuration. Only in this configuration we had the flame. And again, for gas recirculation, again, I mean, ROH is smaller combustion volume, that's why you have lower gas recirculation. But in this configuration, your air jet turns on both the sides. So that's why you have less fraction of gases which are recirculating from fuel side. But that we can reduce by reducing this dimension, and then most of the gases are recirculating from the fuel side now. So again, if I do step input of tracer at fuel inlet and then track what happens to RO configuration and RO high intensity configuration, I definitely find that this high intensity configuration will have a lower residence time for most of the gases, so which may result in higher CO levels. And anyway, your average residence time is also low for ROH configuration. And if I see OH star distribution, one thing I can note is that my reaction zone is mostly, so it is not dancing around inside the combustion chamber. It is mostly confined to a region which is near the bottom of the combustion chamber, and that is the same story for higher intensity combustor also. So this may be beneficial. And once I start injecting fuel in the cross flow, so my reaction zone actually starts getting closer and closer to the fuel jet. So this also means that, I mean, this configuration and this configuration will allow more time for gases to convert from CO to CO2. So I may have lower CO emissions for these configurations. So now coming down to the bottom line or baseline, what happens to NO and CO emissions? And I also have results for lean operational or lean blow-off limits. So here is a summary of for NO emissions for all these configurations which we investigated. So here is the premixed configuration, and then we can see that for these non-premixed configuration, there is a huge gap. I mean, in this forward flow configuration and in this reverse flow configuration, there is still a big gap between premixed mode and non-premixed mode, and then we want to bring these non-premixed mode closer to this premixed modes to reduce the NOx emission. But if I see the reverse cross-flow configuration, in reverse cross-flow configuration, even in non-premixed mode, my emissions are very close to premixed flame mode. So even in this non-premixed modes, I am able to achieve some of the combustion characteristics which are closer to premixed mode. So I don't have to premix fuel and air, but I can achieve those characteristics by injecting fuel smartly. And these are CO emissions. Again, very high CO emissions for forward flow configuration, possibly because it doesn't have enough residence time to convert to CO2. In reverse flow configuration, I have slightly lower CO emissions, but in reverse cross flow configuration, I mean, your CO emissions are pretty close to your premixed flame mode configuration, and then quite low. So coming to lean blow-off limit or lean operational limit, so the benefits of lower NO and CO emission does come with a penalty, that even in non-premixed mode, your lean blow-off limits actually increase as I go closer and closer to premixed mode. So in premixed mode, for example, for this reverse flow configuration, in premixed mode, the blow-off limit is equivalence ratio of 0.6, and our configuration RC1, which resulted in best NO and CO emissions, this lean blow-off limit was also closer to premixed mode. So actually this configuration is operating very close to premixed mode. So that's why we also have to give penalty of having higher blow-off limits. So that's it. So to conclude, I mean, we have investigated both forward and reverse flow configuration in both non-premixed and premixed flame modes. And then we observed that some of the configuration we cannot sustain flame experimentally. I mean, you just don't have to inject fuel and air inside the combustion chamber and expect that it will burn. You have to smartly design your combustion chamber and smartly design the gas recirculation inside the combustion chamber to get a stable flame. And then for forward flow and for both forward and reverse flow configuration, your reaction zone is situated at different locations, and then this depends on your flow field and as well as fuel air mixing inside the combustion chamber. And in the end, we found that reverse cross flow configuration was most desirable. It gives best combustion characteristics of lowest NO and CO emissions among all non-premixed configuration. And then this operated in very closer to premixed mode. So even if you are injecting fuel and air separately, you are getting characteristics which are closer to premixed mode. So I would like to acknowledge support. So this work was supported by ONR, and then I would like to acknowledge support from Dr. Gabriel Roy and Dr. Bedford for their support. So thank you very much.
Thank you, nice presentation.
Thank you.
We would like to have some question or comment. I have a question. I would like to know the effect of reverse and forward flow on the exhaust emission.
Mm-hmm. On the emissions, NO and CO emissions. Yeah. So reverse flow configuration mostly gives lower CO emissions. So I mean, your flow has to turn and then exit the combustor. So it will have more time for CO to get converted to CO2 because it has a longer path to trace. So mostly reverse flow configuration gives lower CO emission as compared to forward flow. That's what we have been observing.